Good morning, everyone. In the previous class, we were discussing about the how we can perform the different operations like write operation, read operation, and the hold operation with the SRAM cell. Now, in this particular lecture, we will talk about if we are performing some operations with the memory, then how we can calculate the margin or how much noise it can tolerate, or simply suppose because we are storing some logic on storage node of the memory. Okay, and we want like the memory, whatever the data we have stored, that should be fixed. Okay, so there should be no variation, there should be no change. It should the data should not flip. Okay, but all these things which I'm saying, like whatever the data we had, that should not flip, that depends on what is the stability of that memory. Okay, while reading the data, while writing the data, or while holding the data, the stability play a major role. Okay, so if the stability is very less, in that case, the probability of flipping is very high. Okay, and vice versa. So the ideally the stability should be as high as possible. Okay, and if we are able to achieve the maximum stability, then in that case, the like robustness will be better for the memory. Okay, so here we'll talk about how we can calculate. Like suppose in the previous class we discussed about how we can calculate the noise margins and other things, but in the detail, in the like in this particular lecture, I will talk about how we can calculate what is the simulation setup. Suppose you want to calculate the memory, you want to suppose you want to calculate the write noise margin or read noise margin. In that case, how you have to calculate it, how we need to sweep the data or the storage node, so that you can get some butterfly curve. Okay, so here I will be discussing about something like that. Okay, so let us try to see. Suppose I have a 60 SRAM cell which looks like this one. Okay, and if the 60 SRAM cell is something like that, and here if we see, we have two inverters. Let us assume this is the inverter number 1. Okay, inverter 1, and the second inverter we have here, which is the inverter number 2. Okay, so we can have a two inverters here. Now the question is how we can calculate the noise margin. Okay, noise means simply like suppose if we are externally providing some noise at the storage node, because see, let us assume this q is equal to 0 and q bar is equal to 1. So let us assume if this is the data which we have stored, but if there is some noise, there is some external source which we have provided at q, which is changing from 0 to 1. Okay, and if it is changing from 0 to 1, what it means? It means that the strength of this node q will increase, and if it is increasing, that will force to turn on or to change the logic by this inverter number 2. Let me repeat it again. Suppose if we have some data which is stored at node q, and that is 0, and at qb it is like logic 1, and suppose if somehow if there is some noise and it is changing, like if the storage node q is changing from 0 to high, just like RAM. So during the initial phase of change, there will be no change, like the data will be same. Okay, but once this will reach up to certain threshold voltage, might be the change at q will trip the logic at qb. Okay, so because this q will act as an input for this inverter number 2, and if this is more than trip point voltage of this inverter number 2, if the voltage at q is more than the trip point voltage of inverter number 2, in that case that logic will change, and if qb is changing, that will again trigger this q to settle down to the other state. So this is how we are going to create the noises. Okay, so let us try to see how we can do that. Okay, for that purpose, suppose here we have this is nothing but this is the same circuit which we have made here. Okay, just I replace the inverter with a symbol. if you see, the upper one is nothing but like here, if we have a, let me change the color. If this is the Q and this is the QB, in that case, the upper inverter will be nothing but this will be the inverter number 2. Okay, based on the circuit which we have made here. So this is nothing but this will be inverter number 2, and the lower one is nothing but this is the inverter number 1. Okay. This is how simply, if you see here, inverter, the input of inverter number 2 is Q and the output is QB. So inverter number 2 input is Q and the output is QB. That is why we have decided Q inverter number 1 and 2. Okay. Now, I just told you, because we need to add some noise, like the pictorial representation can be made in another way, something like that. So what I need to do, I need to apply some noise at Q and the QB. Okay, so if we are able to apply some noise at Q and QB, something like that, so the setup could be made like this. Okay, so and if you see here, like there could be some polarity of this noise voltage as well. So the polarity of noise voltage could be like, let us assume the positive is here, negative is here, and similarly positive is here, negative is here. See, in reality, we do not apply any of the voltage sources between inverter and the Q. Okay, this is the pictorial representation that gives, if there is some noise present at this node, then how it will alter the logic of inverters. Okay, that is why this is simple a pictorial representation. Okay, to understand the concept of stability. Okay, in reality, we do not connect any of the voltages over here. We just connect the voltages at Q to save the data. So I already told you how to do that, how to perform those things. Okay, so this is a simple a pictorial representation. Now let us talk about if we have a simulation set or something like that. Okay, and if I want to perform some operations, so what will happen? As Vn increases, the stability of bit cell will change. Okay, so initially if Vn is equal to 0, in that case it will act as before, like whatever the status of the circuit was. Okay, but as Vn increases, the stability of bit cell will increase, and the bit cell stability during active operation, especially like read cycle, that represents a more significant limitations to the SRAM operation than the hold one. Let me repeat again what I'm saying. The first and very important point is, like, the change in this VL will also change the stability of this memory. Okay, if Vn is equal to 0, it means the stability will be same as before. Okay, second point, if we are talking about the stability, then the stability could be in any way, like during the hold mode, during the read mode, during the write mode. Okay, so we have 3 operations, and the stability can be of in any of these 3 modes. Okay, so the bit cell stability during active operations means the read and the write are these 2 are the active operations, and the hold operation is not active, because during the hold we are not performing any operation, we are just holding the data. Okay, but while reading and the writing, what we are doing, if we are reading the data, what it means, we are precharging the bit line capacitors, and then we are reading the information based on the whatever the voltage we have. And similarly, while writing the data, we need to write something. So read and write, these two are the important thing, like the active operations. Okay, these two are the active operations. And the important thing is, like, the stability of memory during active operation play a significant role, because if during operation, if the stability is very less, then the probability of failure will be more. Okay, so the special the consideration must be taken care, especially during the read operation. Someone may ask why I am not saying write operation, because write operation is also active operation. So I will answer this question later on. After 5 minutes, I will tell you why the most of the researchers are considering the read stability, and the read is the significant issue, or the read stability is a significant issue while designing the memory. Okay, hold is not a problem. We can maintain the hold noise margin significantly high. We can also maintain the write margin significantly high. Okay, so write margin is very good. But we always face the problem while reading the data, or while calculating the read stability. Okay, so the read stability becomes a prime concern for every researcher. Okay, so here I will be focusing how we can do that, how we can enhance the read stability and everything. So yeah, enhancing is not in our scope, but how to calculate the read stability, I will tell you. In the next semester, we will be discussing about all these things, like how we can enhance these things and other things. Okay. So as we have shown in the second figure, like we have the noise sources are included and with the worst polarity, and this has been given. As the voltage is applied, like this voltage is applied, the voltage transfer characteristics of this inverter too, like suppose if the Vn is increasing, okay, if the Vn is increasing, then the voltage transfer characteristics will move somewhere here and there. Okay, so let me quickly draw the stability diagram of some of the circuits, which is really important. Okay, so let me do that first. So suppose if I want to make the butterfly curve for the hold operation, then how it could be done? Let us try to see. As we know that during hold operation, this M5 and M6 are in the off state. And if M5 and M6 is in the off state, then let us assume the Q is storing logic 0 and the QB is storing logic 1. Okay, so this is the consideration. And if we have considered something like this, then what will happen? Let us see. If the noise Vn is increasing, okay, so if the noise Vn is increasing, initially the Q was 0, okay, Q was at logic 0. So if the input is changing, like Vn will change. Like if the Q is equal to 0, means QB is at high logic. Okay, so it will act like an inverter. Yeah, simply it will last something like this. Okay, so let us try to make the behavior. So the inverter shown here will look like this one. So this is for the first inverter, and similarly for the second one, let us try to make it something like this. So second one will be something like this. Okay, so this is the butterfly curve which we have drawn, and I just told you before, like suppose if I have to calculate the noise margin, so this is how we simply need to find the maximum size square that can fit into the measure lobe or something like this one. Okay, so this is what the hold static noise margin in this side, whatever we have here, this side is called hold static noise margin. Now, because I have already discussed this thing, how it can be changed, like if the sizing of the transistor is changing, then this curve will shift left and right direction, and this measure lobe will also change. Okay, so accordingly we can do that. So this is what we can call the hold static noise margin. Similarly, if I'm performing the read operation, then how it can be done. Okay, so let us try to see the read operation. Okay, during read operation, what we generally do, we generally connect the BL and BLB at logic high, because we need to pre-charge the transistor, bitline and bitline capacitor transistors we need to charge. And if we are charging bitline capacitors, then what will happen? Because see, I just told you the read stability is very low. Okay, the read stability is very low. This is only because there is a voltage division between the excess transistor and the driver transistor during read operation. Because see, if I'm reading the data from the memory. So what we are usually doing, whatever the bitline capacitors we have over here, these bitline capacitors are charged, and based on the state, based on the logic which is stored at Q and QB, this bitline capacitor either it will discharge or it will be remain same. Okay, so if the logic the stored logic is high, in that case it will be remain same. Like see here this bitline capacitor is, second bitline capacitor is charged, and here we have the logic 1, so this bitline capacitor will not get any part to discharge it. Okay, so this second, like CBLB will not discharge, but this CBL, this will discharge. Okay, so if it is discharging, so yeah, so and if it is discharging, this M5 and M1 will be responsible in the discharging one. Okay, and they are creating some voltage division kind of things, and because of that the stability during the read operation is less than the hold one. Okay, during hold there is no division, just we are changing the inverter characteristics if from Q and QB only. But during the read operation, the excess transistors are also involved. Okay, and if excess transistors are involved, in that case we will not get a complete swing. Might be there could be a less swing than the inverter. Okay, and because of that the noise margin reduces. Okay, so
Hello, sir.
yes, please.
Sir, please like repeat this point, like M1, M5 on.
Okay, so if suppose I want to perform the read operation, so in the last lecture I have already discussed like how we can perform the read operation.
Yes, sure.
Okay, so for read operation what we need to do,
The BL is 1 and BLB is 1.
both are one, and the both bitline capacitor should be charged. Okay, so let us assume CBL and CBLB, like here we have a CBLB. This both the capacitor will be charged, and if both the capacitors are charged, and now what I have to do, I have to connect one sense amplifier between bit line and bit line bar. Okay, now if I have connected some sense amplifier, then what will happen here? Because Q it as logic 0, so this bit line and Q is at logic 0 and the QB is 1, so this QB will activate this transistor M1, and M1 will be in the on state. And because we have provided WL is equal to 1, so M1 is also in the on state. So M1 is in on state, so M1 and M5 is in the off state, on state. If the both the transistors are in on state, this CBL will get path to discharge it. So it will discharge through this one. And because the if during this read operation, if I'm increasing this noise, because these capacitors are discharging, okay, this capacitor are discharging through M5 and M1, and I'm increasing this noise Vn. Okay, so if I'm increasing this noise Vn, in that case stability will not be same, like the characteristics will not be same, because we are like suppose let us assume I have connected some voltage noise over here. Okay, and I'm increasing the voltage from 0 to 1. So I'm trying to charge this Q voltage through this noise, and this CBL is discharging through M5 and M1. So the noise is charging this Q, and because the M5 and M1 are in on state, so they will try to discharge it. So might be the characteristics will not be same like an inverter. It will never be reach at logic 0, because this noise will force the Q to maintain the logic at high. But this because of the strong M1, might be this will start changing the logic. So this is the reason like why it will give the inverter characteristics but not perfectly, and why the stability will reduce. Let me finish this graph and then I will tell you how it is happening actually, right? So suppose give me 1 minute, then might be your question will be answered, so you don't need to ask the question after that, might be. Okay, so let us try to see. Suppose while reading the data, because this M5 and M1 is involved, the voltage division kind of things is there, so the read stability will be less, something like that. So how the behavior will look like? Behavior will be something like it will try to discharge it, and might be it will not discharge, and it will read something like this. The 100% discharge may not be possible, because this noise will force to maintain this logic Q at high, and here this M5 and M1 will try to discharge it. Okay, so like M1 and discharge the CBL. So both the things will happen. So this is how the behavior will be something like this. Okay, so and similarly, like in opposite case, if we see in the opposite case, the behavior will be something like this one. So it will sorry. Might be, it will be something like this. Oh, I made some mistake. Okay, so this is how the behavior will look like. Okay, so if you see here, the size of lobes are not same as the whole noise margin because of the involvement of M5 and M6. You got the answer? What you asked?
A little, sir, means like in hold operation, then the noise will like not play any role.
No, noise will play a role because, but the important thing is because during the hold operation there is no involvement of these excess transistors, because this excess transistor will be in off state, and if these two are the off state, they will simply act as an inverter. Something like if I am if I have connected some noise voltage over here, okay, and if I'm increasing this one, so simply this noise voltage will trigger this inverter number 2 to change its logic. And similarly, like if I'm applying some noise voltage at QB, so it will force to change the logic of inverter number 1 only. So there is no involvement of M5 and M6 which will try to hold this one. Okay, and because here we are seeing in the opposite thing, like because here we are discharging, one process is discharging and the second process is changing the logic through noise. So both actions are happening during the read one, but during hold there is no charging or discharging, something like that. We are just simply changing the noise voltage to change the logic. Okay, so that is why they will keep on holding. Yes, here we this potential difference is the important role to reduce the noise margin. So the important thing is like we have to during the read operation, we have to optimize our circuit in such a way that this lower margin, whatever here we are observing, this should be as small as possible. And if we are trying to maintain that thing, like we are trying to reduce this voltage difference, uh, uh, in that case we can increase the right noise margin. Okay, and how it could be done? It could be done by simply changing the strength of this one. Like if I'm able to increase the strength of some of the transistors which are responsible to pull it down, then we can do it. Like see, by increasing the size of M1, if I have increased the size of M1, this will be more stronger. So the we can move up to the 0, something like that. But yes, that will increase the size of memory as well. So these are some challenges, yeah, that need to be considered, especially designing while designing the memory. You got the answer, or still there is some doubt?
Yes, sir. I mean, I got, but I'm not getting like the graph how it is like that. Means it is discharging, then noise is coming. Some little I got idea, not much.
Okay. So now how I should explain this thing. Let me think a little bit.
So can you explain the second graph like only that much?
Yeah, second, the first one is simple. Like the second graph is for the simply read static noise margin. That's it. Let me explain it again. Okay. So for example, initially, let us assume Q is equal to 0 and QB is equal to 1. Okay, and if I'm reading the data, what I have to do, I have to precharge these bitline capacitors. And if I'm precharging this bitline capacitor, so this BL will be at logic high, this BLB will also be at logic high. Okay, so these two are at logic high. Now what is happening if I'm increasing this noise? Let us try to see here. This BL and BLB is equal to 1, and now what I'm doing, but I'm increasing this noise Vn. And if I'm increasing this noise Vn, so because the Q was as logic 0 and QB was at logic 1, we are increasing the positive voltage at Q. And if we are increasing the positive voltage at Q, what it means, it will try to change the logic, like the input of this inverter to will try to like it will become more positive than before. and the vice versa, like so if it is happening something like this, then what will happen? uh, uh, and after certain voltage, like if I keep on increasing this noise voltage, this is something, this is nothing but this is the noise voltage. If I keep on increasing this noise voltage, the characteristic will act as an inverter, simple inverter, because this is simple inverter and I'm increasing the Vn. So this will act as an input of this inverter number 2, and inverter number 2 should change its logic, something like I'm changing the input, then output will be something like this. So this is the ideal characteristic which I want. But why there is some gap over here which I'm showing here? Okay, the response, the gap, this gap is due to because of the involvement of these excess transistors. So this excess transistor, because the voltage which I'm increasing here from 0 to 1, so this Q voltage, see, suppose if there is no involvement of this transistor, in that case this Q will change from 0 to 1 at some period, after some time. Okay, but because this transistor during the read operation, this excess transistor and this pull down network, like pull down transistor M1 and M5 both are in on state, so this voltage will try to discharge it. And if it try to discharge it, and noise will try to charge it, so what will happen? The charging and discharging both will happen at the same time. Okay, so the Vn will try to pull it at logic high, and this because of the active M5 and M1, this will try to discharge it, so the 100% discharge may not be possible. Okay, because the Vn we have kept like this noise is at very high, like it is logic 1. So this is how this will try to maintain it, and there will be some potential difference, something like that. Try to see it, because we need to finish something.
Yes, sir, I got it.
Okay, so in case of any doubt, might be we can have a chat and we can discuss later. Okay, so this is how the noise margin can be calculated during the read operation. Okay, now let us try to see what happens during the write operation. Okay, the write operation is equally important. Okay, during the write operation, what I have to do, I do not like the simulation setups are something different. Yeah, one more important thing that I missed here. During read and in the hold operation, we have a two stable states. Okay, if you see here, this point is the stable point. Okay, this point is one of the stable point, this point is one of the stable point, and this point is the unstable point. Middle one is the unstable point. Okay, so let me mark that one. So this point is the unstable point during the heat. And if you see here, this is the unstable point, and other 2 points like this one and this one, these two are the stable points. Okay, but if we talk about the right noise margin, we have only one stable points. Okay, how it is so, why it is so, let me explain that one. Okay, so the simulation setup for the right noise margin, yeah, one more important thing, let us try to change it. Suppose the characteristics is something like this, and if we are trying to apply some voltage, some if there is some mismatch here, so might be if I'm making, let us assume this the brown one is due to inverter number 2, this brown characteristics is due to inverter number 2. Okay, because see here, the input is Q and the output is QB, so the brown one is this for inverter number 2. So this is for inverter 2, and the purple one is due to the inverter number 1. Okay, now if I'm changing the size of this inverter to improve this one, like this problem, whatever the things over here, so what will happen might be the waveform will shift in other direction, something like that. Let us try to see here. Might be the waveform, this can shift something like this one, yeah, in this direction, and the other waveform may like the and because we are increasing the strength of other ones, so it will be something like this, and the waveform will be something like this one. Okay, so might be the size of this one will reduce. And if I'm keep on changing these noises, then the waveform at some period of time, the waveform will be like this. Okay, and the other part will be something like this. Okay, so this can also happen. And if you see here, this is the minimum noise margin. Like here the instability will come. So before that, because here if we see the second lobe has been this is removed, like there is no second lobe. Okay, so this is how we can manage. So these all things based on the noises. So I will give you some uh, uh, something like some notes, and then you will be able to understand what I'm saying here. So I will tell you. Fine. So let us try to consider the read one. Sorry, write one. So suppose I want to perform certain write operation. Then in that case, the simulation setup is something different than the read one in other things. Okay, so let us try to understand few things. Okay. Basically, read operation write operation can perform when we have the like suppose initially the Q was 0 and I want to write logic 1 at Q. So what I have to do, I have to activate this BL, and the BLB will be 0 and the WL will be 1. So this is the potential which we need to provide. But the important thing is the write static noise margin is like the is the combination of the read static noise margin and the write static noise margin. What is this combination? I will tell you. The simulation setup is done in such a way that, like, if I'm writing some data, I'm trying to write some data on Q, so that I have to provide some noise voltage here. This setup will not work. Okay, for the writing the data, the setup is something like that. Okay, so here I have to provide some noise voltage Vn, positive negative, and that should be that we should apply at node Q, and at QB I have to measure, I have to observe it. Okay, I have to observe it, because see here why I'm saying something like that, because here at node Q we have logic 0. Okay, we have logic 0, and I want to change this Q 0 to 1. So that is why this noise voltage must be increased from logic 0 to 1. So that is why I have to increase this Vn from 0 to 1, so that this Q will be changed. Okay, opposite thing cannot be done. What is the meaning of opposite thing? Means, like, suppose if Q is equal to 1 and QB is equal to 0, in that case Vn cannot be applied over here, because Q is already 1. So why there is a need of change from 0 to 1? So there is no it is not possible to swap the logic. Okay, so that is why we need to apply the noise on the node where the logic is 0. Okay, so 0 will be here and 1 will be here, and we need to observe accordingly. We need to observe the output accordingly. So this is the setup for the write stability. Now let us try to understand how it could be done. So during the write operation, this the voltages like which we have here, like this M1 and the yeah, let me write few things over here so that will be better. Okay, yeah, here. So during write operation, this M5 and M3, because that will form a resistive voltage divider network for the BL, and M5, M4 and M6 that will form a resistive divider. Like we know that while reading and writing, this pull-up transistor and the access transistors are responsible. Okay, so that is why this M5 and M3 will form a resistive network. And similarly, M4 and M6 will form a resistive network while writing the data. Okay, so during the write operation, this M3 and M5 that will form a resistive voltage divider for the BL and the storage node Q. And similarly, this M4 and M6 will form a resistive network for this BLB and storage node QB. So this is the important thing that we should consider. If the voltage divider pulls this Q below the trip voltage of this inverter, like whatever the voltage divider over here, this is nothing but this is the input, like this is giving like Q, whatever the Q we have. And if this Q voltage is sufficient enough, that is more than the trip point voltage of this inverter. Like if I'm changing this voltage Vn in such a way that it crosses the trip point voltage. Trip point voltage is nothing but the voltage at which the logic is changing, something like that. So this voltage is the trip point voltage. Okay, and if the voltage divider is, while writing the data, if this Q is above the trip, like a trip point voltage or the below the trip point voltage, so it will change the logic. Okay, so if the voltage divider pull the Q and QV below the trip point voltage of inverter number 2, then the successful write operation can be occur. The write ability of this SRAM cell can be calculated with the help of write static noise margin. Okay, and the write static noise margin is extracted by a combination of read voltage transfer characteristics and the write voltage transfer characteristics, because we have two phenomena. One thing is like here, because while writing the data, we have two nodes which are opposite in nature. See here, which I just told you, because if the logic is stored at Q is 0, in that case this Vn should be from 0 to 1. But on the other side, we can I cannot apply the noise source at QB like 0 to 1, because the QB is already 1, so I don't need to change it from 0 to 1. Okay, so that is why there is a two different phenomena here in the write operation. Okay, so this phenomena we call it the reading operation, and this phenomena we call it the write transfer characteristics. And if we combine these two things, we will get the behavior something like this. Okay, so let me explain how we will get the behavior. I will share some notes about this one, so that might be if there is any doubt, then you can read it.
Sir, we are not in control of the noise, right? Means it can
Which
be
one?
anything.
We are sorry. What you said?
Sir, like you said that here the noise I want to increase, but we are not in control of the noise, right? Noise can be anything.
No, let me clear this doubt. Whatever the simulation setup we change over here, this so this noise is simply a just model. Like if this voltage is changing, then how these characteristics can change. Okay, so and based on that we can define the stability. Okay, so this is just a pictorial model. And because see, if let us assume if I have an inverter something like this, which is giving a characteristics like this. Okay, and second inverter which is giving something like a lower low. So here stability is less. Okay, so stability is less means that with the small voltage of Vn, that might be that can flip the data. Okay, so the noise margin is simply how much noise it can tolerate, how much fluctuation it can tolerate. So the noise voltage, whatever we are considering, this is the conceptual one. It's not exactly like we are applying some noise, something like that. Okay, yeah, to calculate a butterfly curve, we have to apply some voltages which can act as a noise. But in reality, this noise is uncertain. It could be anything. Okay, so yeah, it is absolutely correct like while simulation, while calculating, we need to apply the real voltage to change the logic. But in reality, to make it stable, we must have yeah, additional noises, can be anything, and that can alter the logic. So we don't know what kind of noise it is. Okay, so but we are simply assuming like the noise which we are getting, that is simply increasing the voltages at input of both the inverters. So this is what we can understand, or we can assume. Okay, you got the answer?
Yes, sir.
Okay, fine. So now let us talk about how the characteristics during the write operation will look like. Okay, so the write operation, the characteristics, because I just told you we have a two kind of operation. One is the read kind of things, and the second one is write one. So if the Q is storing logic 0, in that case the read kind of operation can be performed. That is because simply I have to increase what is happening. I need to increase the input voltage. I need to increase the noise voltage from 0 to 1, and that will be done. Okay, so this is what we have to do that. So at Q, that will be like read voltage transfer characteristics, and at QB, that will be the write voltage transfer characteristics. So the graph will be something like this. Okay, so this is because of the read static noise margin, read voltage transfer characteristics, because the setup is something like a read one. Okay, and on other side, because QB is already 1. Okay, and if I am changing it from 0 to 1, so there is no meaning. So it will reduce some voltage, but it will be something like this. Okay, so this kind of behavior will be observed. Yeah, I don't know why this is coming. Let me this thing, there is some problem. Yeah, no, it's fine. Okay, so this is what the behavior we will observe while writing the data. Okay, so something like that. There may be some doubt, might be why we are getting this kind of behavior. The simple thing is like if we have Q which is at logic 0, and I'm increasing the voltage from 0 to 1. So this is absolutely possible. Like we can do it. We can change the logic from 0 to 1. But because the QB is at logic 1, okay, QB is at logic 1, and in that case we cannot change 0 to 1, because see, this kind of noise is not possible. Initially the output was 0, and the noise will start from 0 to 1, not possible. So even though if we are applying something like that, so there will be a small deviation because of some charge changes, but it will be something like this only. So there will be slight change, but it will not be like this. Okay, it will not be like this, because it was at logic 1 well before, so we don't need to apply anything. So this is how we can get the characteristics. The important thing is like how we can measure the noise margin. In this case, to measure the noise margin, we need to simply find the maximum. Yeah, that is why I just told you in the write noise margin, or the while writing the data, we have one stable points, like that is why we can call them the monostable points. So we need to find some place where we can have a maximum square. So let us assume the square, no, not at this point, might be we can get somewhere here. So anywhere you just need to locate it where you are getting the maximum sides, and that will be the write noise margin. Okay, so this is how you can calculate it. So these are something that you should know. Okay, so yeah, this is all about the noise stability calculation during all the operations. So this is what we call the write static noise margin. Another parameter like the right trip point is the in the previous graph we can see like the writing to calculate the right noise margin is not that much easy, like so it is something like we have a single stable point, so we need to check it properly and proper simulation setup is needed, right? So to avoid that thing we can have a other way to calculate the right stability, and that parameter is the right trip point. What this right trip point is, so I will tell you. So the right ability of SRAM bit cell can also be characterized by the right trip point voltage, okay, and that is defined as the maximum amount of voltage that is needed on the bit line to flip the bit line content. Okay, so whatever the bit line content we have, suppose I have a memory cell, something like this, okay, and what I am doing, consider the q is 0 and qb is equal to 1. In that case, what I have to do, I have to apply the WL is equal to 1 so that M5 and M6 will be on, because we are writing the data. So while writing, the WL must be 1. Okay. And the bit line should change from 0 to VDD. Okay. So if I'm changing the bit line from 0 to VDD, so the that will change the logic. Okay. So so I will tell you, let me try to draw it. Suppose I have this bit line voltage here. WL1 was at logic high. Okay, so initially the bit line 1 is something like this. Okay, so if I will change the bit line voltage, then what will happen? Bit line voltage will change something like this. Okay, so this is, let us assume the bit line voltage is changing from this to this one. Initially, I'm assuming like Q was 0 and QB was 1. And because the bit line is changing from 0 to 1, okay, so this bit line is changing from 0 to 1, and Q was initially 0 and M5 is in on state. So after a certain period of time, this Q will flip its logic from 0 to 1, because the bit line is changing from 0 to 1. So after a certain period of time, after the trip point voltage, right trip point voltage, this Q will change its state from 0 to 1. Okay, so let us see how the behavior will look like. Okay, so initially the Q was logic 0. Okay, and it was something like increasing, something like this, and suddenly once it crosses the trip point voltage, the voltage will become something like that, like the q voltage will become something like that, and that will be maintained for the rest period of BL. And similarly, because the BL is changed, so BLV will also change. So the BLV will look like this one. So initially the initially the QB was at logic high, but it will try to discharge, and might be it will suddenly flip its logic to this point and something like this. So this one is the QB, and this one is the Q. Okay, so if we see here, we have one point at which the logics are crossing here. Okay, so this is the point at which it is crossing. So what I need to do, I need to project it, what is the voltage at this point. So this is the bit line voltage at this point. Okay, important thing is like you should know very well. Let me change this status so that might be this doubt will be clear, otherwise you will face some problem. Let us assume make it something like this. It is not a good characteristics, because it is not possible. Ideally it should flip at 50% value only, so that will give a better characteristics. But yeah, to understand these things, I have just made like this one. Okay, so this is the point at which it is crossing. Okay, and project the voltage of BL at the same time. Okay, so the BL is something like, let us assume this is the BL, this is the point, this point is the BL. So the difference between this point and the maximum voltage, this we call it the right noise margin. Okay, and the point where the logic was tripped, the minimum voltage, the minimum voltage of the BL at which the logic was tripped, we call it the right trip point. Okay, this right trip point and these points, like the right noise margin, this depends on the pull-up ratio and the cell ratio. So if the pull-up ratio is different, then might be this waveform will shift left and right, and similarly for other cases. So this is how this will look like. So based on that, we can calculate the right noise margin, and the right noise margin nothing but this is the VDD minus VTP. VTP is nothing but which is the trip point voltage. Yeah, so here if we project over here, so this voltage is the VTP. So the VDD is the maximum value which we have achieved over here. So this is the VDD. So VDD minus VTP. Yeah, so simply, this is also like you can calculate this one. So in the other way, you can, yeah, this is also VDD. So you can calculate this noise margin. So this is one of the way to calculate the stability during the right one. So let me repeat it again quickly in 1 minute, and then I will close this session. The right trip point is another way to calculate the right stability. In that case, what I have to do, I have to consider any of the storage node like Q is equal to 0 and QB is equal to 1. So let us assume Q is equal to 0 and QB is equal to 1. So what I have to do, because I have to write the data, so the WL should be 1. And because I want to change the logic of at Q from 0 to 1, in that case, I need to set the voltage BL or BL voltage from 0 to 1. So here what I am doing, BL is changing from 0 to 1. And if it will cross the trip point voltage, like BL is sufficient high to change to change the logic of both the inverters. So initially, because the QB was high, Q was logic 0, so the Q will start increasing and the QB will start decreasing at some period of time, they will cross each other, because they will like the trip point voltage will achieve, and after that they will cross each other. So the point at which both are crossing, and we will measure the voltage on BL voltage, and that BL voltage is the right trip point voltage. Okay, the VTP. And once we got this VTP voltage, then we need to find the difference between the VDD, which was here, maximum voltage, and this VTP, which was here, and that we can calculate the right noise margin. So this is one of the easier way than the previous one. You don't need to calculate the square or on the measure low to calculate the noise margin. Simply you need to find this voltage where QB and QB are crossing to each other, right? So, and after that you can calculate this BL voltage and then subtract it from the VDD, and then you will get the right noise margin. So this is one of the alternate way and the simple way to calculate the right noise margin.